Welcome. So, we have already discussed the link power budget and obviously related to the noise and interference, and now we are going to discuss about the propagation channel through which this signal pass through. So, next couple of classes we will continue our discussion on the propagation channel, what happens. This is a big subject. There are a lot of research papers and PhDs have been done on that. So, we will take up not the physics part of it, we will assume the physics part of it, and what is the effect we will try to see, and our main interest will be how to mitigate those effects for a communication purpose. So, let us start. Satellite communication system propagation. In these couple of lectures, we will cover the effects of the signal propagation through mainly two spheres, that is ionosphere and troposphere, and then we will see some models for attenuation prediction, and then what should be the different mitigation techniques so that we can do proper communication with a good quality of service. Now, ionosphere is from our school days we are aware that they are high above the Earth's surface, of the order of 700 kilometers above, that is 1000 kilometer, or even higher above that. The oxygen molecules, they break up due to Sand's effect, and we have free electrons and ions that move around. And since they are charged particles, obviously they try to follow the magnetic effect of the Earth, that is from the equator to the pole. The magnetic lines they will follow depending on the type of charge. So, therefore, during the day the density of these ions and electrons vary at different places, and obviously by the time initially they are generated with the sunlight, and then by the time they travel higher latitudes, northern and southern, sunset occurs and slowly they recombine. So, near the pole there is not much of effect. Maximum effect is near the equator, that equatorial region, and mid latitude region, some effects are there. But let us just summarize the effects what is seen there. The electromagnetic wave which comes from the satellite, or which is going from the ground to the satellite, they interact with these free electrons in this ionosphere, and the effect of interaction is proportional to the inverse square of frequency, 1 by f square. This is very important for us when we do low frequency communication of the order. When I say low frequency, it is of the order of megahertz and tens and hundreds of megahertz, then the effect is dominant, whereas as we go up in the spectrum in the gigahertz region, particularly in satellite communication, most common is a Ku band, which is above 10 gigahertz. So, at 10 gigahertz the effect obviously will be very low. So, some of them are effects are, it will change the propagating wave velocity. So, when the signal passes through this ionosphere, because of the interaction, it will go not with the velocity of free space, which we assume velocity of light, it will slow down. This slowdown will have some delay effect. For general communication, what we are talking that is for video reception, video broadcasting, data communication, or audio communication, this delay is it's tolerable. But when we introduce this delay for calculating something else, which is done in the case of satellite navigation, satellite based navigation, then this delay is very important. This delay, through this delay we calculate the range. But anyway, even if some effect is there, that at higher frequency, as I mentioned, that since it is 1 by f square, this propagation delay is a very small effect. It also changes the polarization. The electric field vector will get rotated, which is called Faraday rotation, and at 10 gigahertz it is about 1.1 degree, very very small. So because of this depolarization, whatever the residual vector which remains in the intended polarization, that is reduced by a very small amount. So the polarization depolarization effect, of course it will create certain cross polarization component, which is also very small amount because of the small degree of rotation. But this is just a typical number. It varies, as I said, from place to place, time to time, depending on the total electron content or the density of the electrons through which the signal is passing through. There is some absorption, which we can call it attenuation. This is at 10 gigahertz, it's very very small. You can see it is of the order of 10 to the minus 4 dB, very very small. And there is some effect which is called scintillation. Scintillation is a small time effect in a small region, just like a bubble going up in a liquid. Bubble is moving around in a liquid. You can think of a similar concept. Bubble is actually air and or gas inside a liquid. Here it's a dense electrons, free electrons, localized, is formed because of some perturbation, and they again disperse. So when they remain nearby, and through that if the signal passes, then it will have this effects dominating, like polarization will change, the absorption will change, and this absorption will vary peak to peak 4 dB possible at 10 gigahertz. So this is a very short term fading, and this may be of interest to us, but this has to be countered. But in general, the effect at 10 gigahertz is very very low for the ionosphere. So we can neglect this effect for the time being, but for detailed calculation obviously it will come into picture. Now let us see what happens in the troposphere. Here is a just a sketch picture where satellite is shown, and there are certain clouds and rain formation, and then rain's precipitation is taking place, and as if a signal is passing from satellite to Earth or Earth to satellite. Here there is Earth to satellite arrow is given. It can be any direction. Signal is passing through this impairment, which is not the clear sky. No clear gas is there. It is water vapor as well as water itself. It is there. Now that will create obviously some attenuation. Here I have listed only A as a atmospheric attenuation, and the received power, say from satellite is coming, or from Earth it is going to satellite, whichever direction, the received power will be the EIRP from the other direction, the transmit side, and receive antenna gain, and that free space loss, or what we used to call path loss, and that is supposed to be clear sky. And when it passes through these type of disturbances like a cloud and rain, then it will have certain attenuation. So power received will be less. So dB equations are very simple. That is PR is equal to EIRP plus the receive antenna gain minus the path loss or free space loss minus the attenuation. This is shown as a simply atmospheric attenuation. But then in addition to attenuation, there is a polarization change also. The water will absorb, the water content or raindrops will absorb some electromagnetic energy. Also it will rotate the polarization. Because of that also there will be some loss. Let us look at those things slightly detailed. Let us see. Before that, let us look at the total communication link in a SATCOM in a very brief way. Let us say it is a packet communication. So packets are queued at the transmit station, and based on the multiple access requirement, the packets are multiple access modulated, and if necessary it is coded, modulated and coded. For this code is for error correction coding, not the baseband coding, and then type of multiple access for many people accessing. We will discuss multiple access and other things later. Just here you just take this word, that is there is a multiple users are accessing. In this case I have drawn only one user, so they have to share the transponder. That is why something called multiple access, the sharing business is there. So these are a certain blocks subsystem in the transmit station. It is upconverted, amplified and put into the atmosphere troposphere, it is going to the satellite. Here the transponder or the satellite I am showing as a simply amplifier. It's actually frequency translator also. It is amplified, but while going up this signal from the transmitter to the transponder, it has certain free space loss or path loss, and also in the uplink there is certain attenuation, as we have shown in the last slide, that the attenuation could be dominant when it is rain or raindrops or water type of things. We will see more details of that. There is some uplink attenuation, and the transponder, it is signal is amplified, frequency translated, and downlink frequency from the transponder to the receive station, it comes through again downlink free space loss and downlink attenuation. Since the frequencies are different, even if the stations, transmit and receive stations, are co-located or nearby located, the downlink attenuation will be different because as the frequency is different. And if the stations are far away, of course the free space loss, and whether the downlink is facing the same amount of water content or different amount of gas or ionosphere, the downlink A down will be different than A up. Then it is received at the receive station, it is down converted, passed to a demodulator and channel decoder, and corresponding multiple access subsystem takes care. So at the input of the demodulator, we have this carrier to noise ratio, which we were discussing in last couple of lectures. The carrier to noise ratio, depending on that demodulator function, will be there, how much good quality or how many errors that will come in depending on this signal to noise ratio or carrier to noise ratio, C by N. And then after that, let us say there are certain packets formed, and those packets will be put into the queue to send to the user. So corresponding to the bit error rate, there will be, based on the size of the packet, there will be packet error rate which will comes out, and based on the packet error rate, the user will look for the quality of service, how many packets are in error. This is a very general, very briefly we talked about one link of simplified satellite communication. Now service quality relation with C by N, before proceeding further, let us just clear certain things. That is, for packet communication link quality parameter is generally taken as packet error rate or packet error ratio. Generally we call it packet error rate, but it is actually ratio, how many are in error out of the total number of packets received. So it is a PER. Now this packet error rate, and we are very familiar while discussing earlier, while you have studied earlier in BTech, that is the BER, bit error rate. In digital communication, instead of signal to noise ratio, we call bit error rate after the demodulator. That defines the quality, how many bits are in error out of so many bits. So when a packet size is defined in a binary symmetric channel, 1 minus BER to the power packet size, and 1 minus of that quantity is packet error rate. So this is a simple relation for packet error rate to BER, and based on the size of the packet. And of course BER is based on our modulation, and that is proportional to the error function, complementary error function, and the energy per symbol by noise power density, ES by N naught. I have called energy per symbol, that is, it could be energy per bit also. So EB by N naught or ES by N naught, whichever way you take it. So BER is proportional to this. Now this complementary error function will depend on the type of modulation what you used, etc. But this ES by N naught is actually talking to us about the energy per bit or energy per symbol, that is the corresponding to the signal power, and this is noise power density. So this is what is important to us. See, if this degrades, BER degrades, if BER degrades, PER degrades. So there is a relation between ES by N naught or EB by N naught to the PER. Let us see the other way, make it a little more clearer. That is, our C by N we were discussing, how much carrier power is received and how much noise power we have received, C by N. Now, C actually is total average carrier power received, that is per symbol multiplied the bit symbol rate, or per bit multiplied by the bit rate. ES multiplied by RS, here RS is symbol rate, or EB energy per bit multiplied by RB, in that case it will be B. So, these two multiplied gives us the C, that is carrier power, average carrier power, and N naught is noise power by the bandwidth. So, this is multiplied with bandwidth, you get C by N, that is N is equal to N0 into bandwidth. So, I can rewrite C by N in terms of ES by N naught, RS and bandwidth as ES by N naught multiplied by RS multiplied by 1 by bandwidth. Okay. Now, so ES by N naught is very important, and correspondingly the C by N naught will be affected. So, let us talk at C and N. Now, atmospheric impairments are attenuation due to precipitation of hydrometeors, that is rain, snow, hail, ice, droplets, etc. Effect is absorption and scattering. You can see that it can absorb, and depending, since it is a different media, that is from free space suddenly it has come, or from air suddenly it has another medium has come. So, from the surface of that particular medium it will scatter. Depending on the rainfall rate and raindrop size, we are mainly dominating thing is rain, we will see, and the loss, that is absorption, will also depend on at what elevation angle and polarization it is coming. We will see a little more detail on that. And many models exist, people try to do model, because this is a statistical phenomenon. So many raindrops are there, it is not deterministic, and the rate of appearing the raindrops in front of the signal is also changing, the rain rate. So, there are many models exist to estimate the average attenuation, and that is done on annual basis, and the location with a known rain rate. So, rain rate is related to the attenuation. People have done a lot of modeling, but this is a very long term basis, annual basis. Now, how much is the attenuation? That is called depth, fade depth. I am using the word fade here. The fade depth are presented as a function of time of percentage. Time percentage, we will see a curve and we will understand that. First, let us look at the raindrops. When rain is ideally created, it is a sphere of water drop. When it is coming down because of its weight to the ground, because of the air pressure, it may take a different form, maybe a ellipsoid. So, in the ideal case, let us take a rain as a ellipsoid. It may tilt at different direction based on the wind speed, wind direction, wind speed, etc. Let us take simply a spheroid, which is a rain drop. It is a major axis, minor axis of that we take, and let us say there is a E vector, that is the electromagnetic vector E field is falling on that raindrop, falling at a particular angle. So, this is E in, E vector, which is coming into the raindrop. There will be some scattering when the transition takes place, but what happens inside the raindrop? This raindrop shape is different. One side, it is the major axis side, it is more water and less water in the minor axis side. So, if I resolve this E in vector into two components, that is horizontal component, here let us take its horizontal, and a vertical component, E v is this much and E horizontal. The horizontal component is more than vertical component in this case, in this particular angle when it is entering. Now, just look at it, that is that E h part will see more water content. So, as water absorbs electromagnetic energy, it will be reduced more compared to the minor axis side, that is E v. So, let us say E h is reduced to this much, whereas E v is reduced to this much. Now, this resulting two vector, when the electromagnetic wave comes out of the raindrop, will have a different amplitude and different location. So, E out amplitude is different than E in amplitude, and there is a theta rotation of the E vector. So, So, you can see there is a absorption and polarization change, and because of the polarization change also there is absorption. Absorption is obviously is there, because of that only the whole thing is happening. So, this general type of diagram showing you that the absorption and depolarization both are happening depending on the shape and size of the raindrop and the direction at which angle the input incident E vector is. So, hope this has given some clarity to you. Now, there is another thing what we get familiar. How do we measure? The measurement is generally available, is called rain rate, and rain rate can be modeled in terms of the diameter of the raindrop, average diameter d is average diameter of the raindrop, the velocity of this raindrop through which it is going towards the earth, that is the precipitation velocity, and d is the drop size distribution, that is in a 1 cubic meter how many such raindrops are there. So, that is the density of the raindrops. So, every either cubic meter or cubic centimeter, whichever way you take the unit, cubic millimeter, whichever way you take, there is a distribution which will vary from spatially, which will vary place to place. So, the model relation is the rain rate is equal to 0.6 into 10 to the minus 3 pi, and the integration of raindrop diameter cube, velocity of raindrop, and the drop size distribution, that will be available in millimeter per hour. And this is a measurable quantity. What is measured, our meteorological departments, what they announce, they measure, and many other agencies also, they measure over an area how many millimeter of rainfall has happened in an hour. So, actually they do it in a different way, but whatever announcement they make, that is millimeter per hour, so many millimeter of raindrop per hour it has happened. So, this gets recorded, and this model is available, that is called rain rate. So, rain rate unit is millimeter per hour, and a model like this is available. Now, it states like that R 0.01 of 40 millimeter per hour. What is the meaning of that? This 0.01% of time of a average year. Every year rain is not same, rain rates are not same. So, year is 365 days, then multiplied by 24 hours. So, in the average year, 0.01% of the time this 40 millimeter per hour rain rate has exceeded. It might have rained at some place only for few minutes 50 millimeter per hour, which is more than 40 millimeter per hour, and some other time half an hour for 40 millimeter per hour. So, like that, those whole year, if you cumulatively add them, and then you can find the 0.01% of the time, that is 0.01% of 365 days multiplied by 24 hours, that is during that much time you can calculate that how many hours it is or how many minutes it is. So, for that much time cumulatively in an average year, rain rate has exceeded 40 millimeter per hour. I repeat, R 0.01 of 40 millimeter per hour is the cumulative percent of time in an average year when the rain rate has exceeded 40 millimeter per hour. It may be 50. So, therefore, for 0.001% of the time, and for less percent of the time, it might have exceeded 50 millimeter per hour. So, it is normally the meaning of this is like that. This 0.01% of the time is generally accepted thumb rule. So, people normally refer rain rate as 40 millimeter per hour, means it is 0.01% of time, but we can go to specifics that for 0.001% of time or 0.0001% of time, this is for very short time. You can see that we might design a system where the attenuation which is happening, that can be taken care for this much time, but we may need a system where my failure or loss of signal should be much less time. So, I should look for a rain rate 0.001% or much lower than that. Okay. Now, you can see the curve here. Of course, there are 3 different frequencies, that is 12 gigahertz, 20 gigahertz, and 40 gigahertz. 3 curves are shown, and for these 3 curves, the total percentage of the time of average year in the x-axis and the attenuation due to rain in dB is just plotted. Let us take any one of them. Let us take the very dominant one, let us say 40 gigahertz one, which is this blue line. You can see that 1% of the average year of the time, that is 3.65 days, the attenuation is 5 dB, whereas 0.01% of the average year, which is 0.365 days, means it is only 0.365 multiplied by 24 hours. So, that many minutes the rain rate has for this rain rate you have attenuation of 20 dB. So, this is much more than for a longer duration of time. So, for a short duration time there may be burst of rain, heavier rain. So, your attenuation during that time is much more. For longer duration time, the burst of heavier rain for short duration are all accumulated together, you can have a lower attenuation. So, your quality of service, that means how much time I can give a guaranteed service that my system will not fail, will not go below the signal to noise ratio or carrier to noise ratio level, you can determine, and accordingly that much attenuation you should protect. So, these are the meaning. You can see that KU band, which is very common band, as we were talking, 12 gigahertz, it is 0.01% of the time is roughly more than slightly more than 5 dB. So, we stop here for the time being, and we will continue this discussion in the next period. Thank you.